All right, today we're diving into the fundamentals of mechanical assembly. We're going to explore the hidden language that, well, literally holds our world together.
I mean, seriously, have you ever stopped to think about what holds everything together? The car you drive, the bridges you cross, it all comes down to putting pieces together perfectly. But how do they actually do that? How is that kind of perfection even possible?
Well, the secret, it turns out, starts with a shared language. And no, I'm not talking about English or Spanish. I'm talking about the language of engineering. And that's exactly what we're going to decode today.
So first things first, let's get a handle on the language of assembly. At the absolute heart of it all is the blueprint, or as engineers call it, the technical drawing.
You know, a technical drawing is basically a universal language. Think about it like a recipe for a chef or a musical score for an orchestra. It tells a technician everything they need to know, the right materials, the exact dimensions, down to the millimeter, and of course, how it all fits together. It is the absolute foundation for any build, no question.
And you know, just like any language has different ways of saying things, engineering has different kinds of drawings. You've got detailed drawings for just one part, assembly drawings to see how they all connect, even sectional views to get a peek inside. But let's take a closer look at a couple of really useful ones.
Okay, so this right here, this is what we call an exploded view. And it's awesome. It shows you the relationship between every single component. It's kind of like taking a super complex machine, say this cylinder head, and just freezing time as you pull it apart in midair. That way you can see exactly where every bolt, every spring, every valve is supposed to go. It is an absolute lifesaver when you're putting something together.
Now, compare that to a schematic. If the exploded view tells you where things go, the schematic tells you how things work. See, this drawing isn't a picture of the physical engine. Nope. It's showing the path the oil takes all the way from the pan, through the pump and filter to all the moving parts it needs to lubricate. So one is about structure, the other is all about function. Big difference.
All right, so once you can read the language, you need the words, right? And that brings us to the nuts and bolts of it all, literally. These are the unsung heroes of engineering.
Look, these are not just random bits of metal you grab out of a bucket. Every single screw, bolt, and nut is a precisely engineered component. And choosing the wrong one, that's not just a simple mistake. It can be a catastrophic failure just waiting to happen.
So let's look at two really common but critical examples. Over on the left, you've got your standard bolt and nut combo. The bolt just passes right through both parts and a nut on the other side locks it down. Simple. But on the right, the bolt threads directly into the second part itself. See? Two totally different solutions for two totally different situations.
So where's the magic? It's all in the threads. The crest is just the high point, the peak of the thread. The root is the low point, the valley. It's that simple spiral design that creates this incredible clamping force that holds everything so tightly together.
But listen, not all bolts are created equal, not by a long shot. See those numbers on the bolt head? They're not just random. They're grade markings, and they tell you exactly how strong that bolt is. An 8 might be fine for everyday stuff, but an 11? That's for super high-stress jobs. Using the wrong grade is a massive safety risk. That's why a good technician will always replace a bolt with one of the exact same grade. No exceptions.
And it's not just bolts. For pretty much any special job, there's a special nut. You've got slotted nuts that use a pin to literally lock them in place. There are nylon insert nuts that fight against vibration, and of course the good old wing nut for anything you need to tighten by hand. Each one is a very specific solution to a specific problem.
Okay, so we've got the plan, we've got the parts. What's next? Well, now it's time to bring it all together. This is the art of the build.
This is really where the rubber meets the road, where theory becomes reality. A skilled technician takes those blueprints, grabs the exact fasteners that are specified, and uses the right tools and techniques to bring the whole design to life. It's a process that, you guessed it, demands incredible focus and precision.
And the process itself follows a few key steps. First up, preparation. You have to clean and inspect every single part. Why? Because any little bit of dirt or a tiny defect could ruin the entire build. Next, you position everything exactly like the drawing shows. And finally, you secure it all, using the right tools and critically applying the perfect amount of force.
But wait a minute, how do you actually know the job is done right? That brings us to our final and honestly maybe the most critical step of all, the quality check.
So, the thing is assembled. It looks great. But is it correct? Is it safe? Is it actually going to work the way it's supposed to? The only way to know for sure is through rigorous quality control. Here's a perfect example of what I'm talking about. What you're seeing is a technician using a straight edge and a feeler gauge. What are they doing? They're making absolutely sure the surface of this engine's cylinder head is perfectly 100% flat. Because even a tiny, microscopic warp could cause a gasket to fail, and that leads to huge engine problems. This is what precision looks like in the real world.
And this really gets to a fundamental truth in all of engineering: the importance of precision. You just can't overstate it. It is literally the difference between a machine that works perfectly for years and one that fails on you at the worst possible moment. Every single measurement matters.
And it goes way beyond just checking for flatness. Quality control is a whole battery of tests. You're verifying dimensions with tools like micrometers, you're confirming the perfect alignment of all the moving parts, and then finally, you're testing the whole thing. Does it run? Does it leak? Does it do exactly what it was designed to do? So, this whole journey we've been on, from the language of the blueprint to the vocabulary of the individual bolt, all the way to the skilled build and the final checks, that right there, that is the hidden system that holds our entire modern world together.
It's a language of precision, of strength, and of function. And it's all around us, every day, even if we don't always notice it.
So I'll leave you with this final thought. Now that you know the basics of this hidden language, what are you going to see differently? The next time you look at a bridge, or a building, or even the engine in your own car, what will you notice? Thanks for tuning in.